given by Felix Wolf. It's a joint work with Malte, Schwerhoff, and Peter Müller. Concise outlines for a complex logic, a proof outline checker for TaDA. Felix, the floor is yours.
Thank you very much for the introduction. So I already said, I'm Felix Wolf, and this is joint work with Malte, Schwerhoff, and Peter Müller. So let's get right into the topic. We're in the context of program verification. So for sequential code, this can often look as follows. We have some code that we want to verify. We formulate a specification and some standard separation logic. And then we use an off-the-shelf verifier which automates the standard separation logic, such as Daphne, Viper, Verifast, Grasshopper. And we use this verifier to then show that the code actually satisfies the specification. Now we're interested in log-free code. So here as an example, an increment method consisting of 4 lines of code. The actual implementation is not really important, just that it's small. Now, to properly provide specification for log-free code, the standard separation logic is not sufficient anymore. Instead, we require a complex separation logic that is capable of reasoning about fine-grained concurrency. And now, due to the choice of the logic, there's also no established off-the-shelf verifier available anymore. All right, that's the setting. So let us take a quick peek at one of our contributions. So in our work, we propose techniques that enable the development of a so-called proof outline checker. It's a tool that can automate the complex logic TaDA in order to verify log-free code with a high automation. But let's get there step by step. So first, the logic. TaDA is a powerful logic capable of reasoning about fine-grained concurrency, linearization points, and environment interference. In the background, you can see the rules, and the purpose of them is essentially just to scare you and to show you, look, the logic is actually difficult, has a lot of difficult proof statements and so forth. Of course, there are other also interesting logics capable of reasoning about fine-grained concurrency, such as IRIS, ICAP, FCSL, and so on and so forth. We're not the authors of any of them. We picked TaDA because we found that its linearization mechanism is best suited for our purposes. Great, so that's the logic. Let's look at the verification side. There's now a trade-off. Fully automated, but severely lacking in expressiveness, we have fully automatic verifier. They have 2 drawbacks. One drawback is that for logic as complex as TaDA, and in particular for TaDA, there doesn't exist such a fully automatic verifier that properly supports the logic and instead only supports a small fraction of it. Furthermore, second drawback is that in order to get that degree of automation, they require often on so-called custom proof search engines. So proof search engines that are built in particular for one front end, which is quite time intensive. Good. So now on the other end of the spectrum, we have a proof checker, very expressive, but severely lacking in automation. A proof checker, as the name suggests, checks the validity of proofs. And again, unfortunately, since the logic is complicated, so are the proofs. So for our tiny 4-line increment method, it requires around 34 total rule applications in order to prove a specification. This immediately means that there's a big overhead. It's difficult to get these proofs right. In particular, it requires expert knowledge for even minor details, which is something we want to avoid. Now, the problem is now, we want to have a verifier with sufficient expressiveness to properly support the complex TaDA logic, while also maintaining a high degree of automation. To address this issue, several tools incorporate the concept of proof outlines. A proof outlines, opposed to a proof, contains only the key steps of a proof. So now for our 4-line increment method, this now results in only 3 such key steps. We also applied this concept of a proof outline to the input language of a verifier. This then looks as follows. For one, we write a specification, of course. And then additionally, as the key steps, we classified 4 rules out of all of TaDA's proof rules as what we call key rules. These key rules carry significant insight about the behavior of a program, particularly the concurrent behavior. For these key rules, 4 key rules, the user has to annotate where they are applied, In the example, we can see that with the rule clauses written in pink, some of which require additional arguments. And here, so the three rule clauses are atomic, open, and update. Okay. So with this, we now have the full picture. We have a proof outline checker, which automates the TaDA logic to verify log-free code. And additionally, our proof outline checker does not rely on a custom proof search engine, but instead uses an off-the-shelf verifier. So we developed the techniques, but we also implemented them in a proof outline checker, which we call Voila. Voila takes, well, as a proof outline checker, a proof outline as an input, and then outputs either success, if the proof outline is correct, or reports which parts of the proof outline has failed. It is worth mentioning that Voila, to our knowledge, is the first tool to support linearization-based specification with a high degree of automation. Good. For the remainder of the talk, or for the biggest part of the talk, I will illustrate our techniques that enable the verification of proof outlines. For that, first, we should understand a bit better what a proof outline actually is. So here, consider the full proof for our increment method, written as a proof tree, deductive proof tree. At the very bottom of the proof tree, we have the goal, which is that the increment method satisfies a specification, here written with the precondition P and the postcondition Q. These angle brackets are how specifications are written in TaDA. So now our proof outline gives us two sources of information about this full proof tree. The first source of information is, of course, through the key steps. So here we don't know what's in between, but we know that eventually the atomic rule will be applied. So the second source of information are through the rules that are determined by the syntax. So for instance, loop, assignment, sequential composition, and so on and so forth. So here again, we don't know what is in between, but we know eventually there will be an application in the full proof of the loop rule. So just to summarize this a bit, some rules are fixed, namely the syntax-driven rules and the key rules. However, most rules are still, rule applications are still missing. Some parameters are fixed. This, of course, at the bottom, the specification, but also, as I said before, some of the rule clauses take additional arguments. However, again, many parameters are still missing. And then lastly, of course, none of the side conditions are checked. Good. To illustrate our approach, we will abstract away a lot of the information. In particular, we only care about what's already fixed, which applications and which information is already fixed, and which application is information is still missing. So missing rule applications, we just show in orange. Fixed rule applications, we show in blue, and then fixed parameters, we show in red. And this lets us represent a full proof tree a bit nicer. Good. So now what's our approach? First, we take the proof outline. The first step is to infer a proof candidate. The proof candidate adds all missing rule applications to the proof. It does so by utilizing a combination of heuristics and normal form, about which I will talk a bit later in the talk. Then the next step is that the proof candidate is encoded into a proof encoding of a standard separation logic. In this encoding, we use auxiliary programming state to fix all the missing parameters. And then lastly, we can utilize an off-the-shelf verifier to verify the proof encoding. And if verification succeeds, this means that all the side conditions are checked and also that the proof is correct. Let's talk a bit about soundness and completeness, what this means in this context. So first, soundness. If verification succeeds, then the proof encoding is supposed to be correct, then the proof candidate is correct, and then finally the proof outline is correct. So hopefully rather straightforward. Now for completeness. First, it's very important to mention that our proof outline language has additional restrictions compared to TaDA. These restrictions effectively force that proofs are more streamlined. These restrictions then result that some auxiliary, artificial proofs are not really supported. However, we see it mostly as a positive point, as it, in a sense, gives the user less chances to shoot himself in the foot. Good. But now, if the proof outline is correct, then the proof candidate is also correct, again with some artificial exceptions, but we can ignore them. What's important here is that our inference of the proof candidate never fails. So even though we use heuristics, we always can get a proof candidate out of a proof outline. Good. Then from there, it's again rather straightforward. First, the proof encoding. If the proof candidate is correct, then the proof encoding is correct. And then finally, if the proof encoding is correct, then the verification might verify. Of course, it's only might verify, since the problem is, of course, still undecidable. What can happen is that there's an attainment that the off-the-shelf verifier can't show. And in this case, what is necessary is to, first off, this is reported in some understandable manner to the proof outline or to the user at the level of the proof outline. And then what the user has to do to overcome this incompleteness of the off-the-shelf verifier is to add assertions that cut the entailment into smaller pieces that can be handled by the off-the-shelf verifier. In this talk, I will illustrate how we infer the proof candidate. I will not talk about the encoding. For this, I refer the audience to the paper. Of course, there are many interesting bits, such as that we simulate interference by other threads, and also that we encode a resource label transition system. So, of course, I can only recommend to have a look at the paper. Great. So, how do we infer a proof candidate? Here, we represent that at the top and at the bottom, the rule applications are already fixed. And now the task is to fill in the missing rule applications in between. This is ultimately a proof search problem. It's a proof search problem where the search space is vast. In particular, in TaDA, there are many rules that can just always be applied, which complicates the problem. Furthermore, when we infer an individual rule application, we don't want to take into account the entire proof outline. We also don't want to start reasoning about like all pairs of rule applications and so on and so forth. So what we need is more structure in order to enable local reasoning that allows us to infer rule applications. We enable this local reasoning with two ideas. The first idea are normal forms. Normal forms restrict triples in between fixed rule applications. So here I have two examples. In TaDA, there's this pseudo quantifier that you can see at the end of the two triples. This quantifier quantifies over the interference that the environment can perform. Understanding it at this point here is not really important. But now part of our normal form is that every state must be bound by exactly one such quantifier. So if we look at the first triple, we can see that the state of the pointer x, namely n, is exactly quantified by this one n. So this triple would satisfy our normal form. And then for the second triple, the state of x is n plus 2, meaning it involves two quantifiers and it doesn't satisfy the normal form. Good. If something like the bottom case is encountered as a result of some other rule application, what this means is that we need even more rule applications in order to establish the normal form again. So the second idea that we have to enable local reasoning are heuristics. Heuristics guide rule applications of challenging rules. Effectively, they capture the essence of what is necessary to make a TaDA proof work. Here I try to illustrate again one of such examples in TaDA. In TaDA, it's sometimes necessary to weaken the post condition such that it holds even in the presence of interference by other threads. Here, for this weakening, one of our heuristics tells us when to do that. It's very important that the heuristic is precise. Weakening too often would result, we would get the problem that there are post conditions we should be able to prove, but we can't because we weaken the post condition too much. Weakening too little would cause the proof candidate to be wrong because some side condition would fail, even though it shouldn't in the proof. Good. And now, in order to infer the missing rule applications, we apply these two ideas in the way that we connect the already fixed rule applications to the normal form. And while doing that, we also follow our heuristics. Good. So let's talk about the evaluation. We have evaluated our tool on existing proof outlines from previous papers. The two biggest examples are the ticket lock, which requires intricate reasoning about the interference of multiple threads. And the other biggest example is the driver stack, which is a log-free implementation of the stack. For all of our examples, we have proven two specifications, a strong atomic specification and a weak non-atomic specification. The atomic specification requires essentially all the features that the tool supports, whereas the weaker specification only requires a smaller subset. Our additional our rule clauses don't cause a big overhead in annotation, at least on our examples. On average, for one line of code, we require 0.8 lines of specification. Most examples take between 1 to 5 seconds, except the biggest examples. And then furthermore, we also seeded on some of the examples, we seeded some errors on which we measured that our implementation has a stable performance. The stable performance on errors can be a problem for techniques based on custom search engines. Voila is on GitHub, so feel free to have a look at that. And with this, I say thank you, and I'm done with my presentation.
Okay, thank you very much, Felix. Very nice presentation, very good one. We have time for 1 or 2 questions. Oh, please raise your hand and we can ask directly. Felix? I have a question from the user point of view. How complex are these annotations and what kind of skills do you need in order to write this annotation and to get a proof?
You can see our proof outline language as a simplified version of the TaDA logic. So you still need to understand, of course, the concept in it, so meaning linearization points, what it means to abstract some code to a linearization point. But having some of these concepts is then actually sufficient, or we believe is then actually sufficient to write these proof outlines.
So is it needed to know the TaDA logic?
No, you could learn Voila without knowing the TaDA logic. I mean, you would have to learn it by itself, of course. I mean, you can't just do it immediately, but no, using the tool does not immediately require that you know the entire TaDA logic.
When the outline fails, the tools give some hints how to continue?
Yes. What we do is we associate every error to some part of the proof outline, and then there essentially map back the error in a way that you can understand it with the abstraction. It was really important for us that we provide an abstraction boundary that protects user of the tool from the details of the encoding, because I mean, there's where the heavy machinery is going on that requires full knowledge, expertise of the TaDA logic, and in order to shield the user from that, it's important to even to also back translate these errors carefully.
Yeah, good. And is it possible to integrate with a real program language?
At this point, I would describe Voila, the tool itself, more as a prototype. The techniques itself, I mean, of course, this is now more, should be seen more as more opinion, but the techniques itself, I believe, should almost be sufficient to use them in a real verifier. There are some limitations, but these are mostly caused by just being not optimized. And what else? yeah, more. I guess that it's, if I were, let me rephrase it. If I were to employ Voila, and I want to use it essentially in a, let's say, real world code verifier that they can use to verify real world code, I think there would still be work necessary in order to provide nicer abstractions that are a bit more distance from TaDA, because we, at the end, we try to stay close to TaDA as much as possible, but there are, I think, a few things that I think could be designed a bit nicer, but this is more at the level of language design and less at the level of really techniques in the background.
Okay, thank you very much, because the time is
Yep.
spinning. Thank you very much again, a very nice